Yeah, Bismillah ar-Rahman ar-Rahim. So we are starting today by a numeric example, which is related to humidification, dehumidification, desalination. We'll read the problem first, and then we'll start the analysis. You may, if you wish, make either open the Blackboard and open the PDF file, which is in the HDH folder, or at least you can take like a screenshot, because we are going to remove this this problem header in a while after we read it. So it says consider a closed air open water HDH modified air heated cycle. So remember that air cycle is closed, water's loop is open, and it is a modified air heated cycle. What modified air heated cycle means? It means that we are locating the heater after the air leaves the humidifier. The cold water enters the humidifier has at a flow rate of 0.07 kilograms per second and temperature of 30 degrees centigrade. So this is the condition of cold water entering the dehumidifier. Then humid air enters the dehumidifier at a temperature which is the maximum temperature. Remember, it's a modified air heated cycle. And for this sort of cycle, air enters the dehumidifier at the maximum cycle temperature. So we are given here the air temperature and humidity and the enthalpy, which is 226.6 kilojoules per kilogram. Air leaves the dehumidifier at T air of 32.31 degrees centigrade, and omega is 0.03118 kilogram vapor per kilogram air, and enthalpy of 112.4 kilojoule per kilogram. There's something that we may notice while we are reading the problem statement, is that I do not want you to go to the psychometric chart or to the EES to calculate it. This actually is an exam problem. If this problem is a homework problem, I would not give this kind of information. I would tell you, for example, that the temperature of, or the conditions of the air entering to the dehumidifier is going to be a T maximum of 80 degrees centigrade, and I will just stop, so that you would go to the psychrometric chart or to the EES program and obtain the rest of the properties at HAir3 is equal to 80 degrees centigrade and phi equal to 1, for example. So the value of phi equal to 1 would be needed so that you can calculate enthalpies. But here, because it's like an exam problem, I'm giving you the enthalpies because I don't want you to waste time looking in the psychometric chart. The same thing applies for state number 1. I'm providing you with 3 properties: temperature TA1, omega 1, and H1 as well. I would normally provide you with TA1 alone, and then you are going to assume that phi is equal to 1. Then you go to the chart or the EES to obtain omega 1 and H1. The mass flow rate ratio is 2. Why we are provided with the mass flow rate ratio? Because at the beginning of the problem, you recall, or you can look at the second line, we are providing the flow rate of the water. When we provide the mass flow rate ratio of the problem, then basically this is as if I'm telling you the m dot of air, because the mass flow rate ratio is m dot water over m dot air. M dot water is given, mass flow rate ratio is given, so you can calculate the air flow rate. HFG, latent heat of vaporization or condensation, is 2384 kilojoule per kilogram, and normally this value is given so that you can calculate the GOR, GOR. Then enthalpy of the distillate water leaving the dehumidifier is 235.1 kilojoule per kilogram. Normally, if this value is not given, we are calculating the enthalpy of water at the inlet air temperature, enthalpy of water at the exit air temperature, and taking the average between them. Here the value is given right away. CP is given to you for the water, and normally we utilize this CP of water in the humidifier. Then the state of air leaving the humidifier is given by H2. The enthalpy of air leaving the humidifier is given 184.7. Omega 2 is given, and the temperature of air leaving the humidifier is given. So this is specifically detailed information about the states at the inlet and exit of the humidifier, inlet and exit of the dehumidifier. What is needed? Number one, to sketch the system. Number two, temperatures of the water leaving the dehumidifier. If you recall, water enter the dehumidifier at the lowest water temperature. It gains energy from the condensing water vapor in the air, and then it leaves at slightly higher temperature. Calculate the power, which is how much heat transfer is being given to the air. Remember, it's a modified air heated cycle, so we are basically heating the air here. Rate of freshwater production, how much fresh water we are producing in the dehumidifier, the gore of the system, flow rate of the brine leaving the humidifier, and its temperature. And finally, he's looking at the effectiveness of the dehumidifier of the cycle. So these are values that are given for a typical problem that you can see in a quiz or an exam or so. There are three types of HDH cycles that you might be exposed to: either water heated cycle, or air heated cycle, or this one, which is the modified air heated cycle. So what I'm going to do now is that I'm going to stop sharing it. I'm going to open a white screen so that we can solve the problem step by step together. Then for that case, I have to summarize the kind of information that are given. And then what I'm going to share with you is the whiteboard, as you can see it here. And first thing I will do, it was said that the problem is representing a modified air heated cycle. So first I'm going to sketch this cycle. We have a dehumidifier, a humidifier, and a heater in between. Air is going to leave the humidifier. It will enter into the heater. Heater is where we're adding energy in. And this red thing is for the air. Air will be heated to the maximum temperature, and then it will enter to the dehumidifier, where it will be dehumidified, and at the end, air is going to get back again to the humidifier. The conditions are given are state number 1 for the air, state number 2 for the air, and state number 3 for the air. I remember last time we said we are going to call it 1 air, 2 air, and 3 air. On the other hand, we have the water. So we have water coming in here. And we have water leaving and entering in the humidifier to be sprayed. And then it is leaving here as brine. So this is first thing to consider. Then the kind of information that are given to me related to this problem are, I read it again while extracting the information. Consider a closed air, open water, HDH, modified air heated cycle. So the cycle of the water is basically open cycle. You can see it enters here, then it leaves here. Whereas the air cycle is closed. It is rotating inside the unit. There are things that we don't add to the system. Normally, we don't add a pump or a fan to the system because we are not analyzing the conditions before and after the pump or before and after the fan. The cold water entering the dehumidifier has a flow rate of 0.07 kilogram per second, and it is coming at a temperature T water 1 of 30 degrees Celsius. Humid air enters the dehumidifier at a temperature, so T air 3 is 80 degrees centigrade, and by the way, this is our maximum cycle temperature. And H air 3 is given as 226.6 kilojoule per kilogram. Air leaves the dehumidifier at T air 1, so state number 1 is given here, at a temperature (32.3) almost, omega 0.03118. It should be kilogram vapor per kilogram of air, and H1 is given as 112.4 kilojoule per kilogram. Mass flow rate ratio is equal to 2. So MR, which is M dot water divided by M dot air, is equal to 2. And we use this to calculate M dot air, which is basically 0.07 divided by 2. And it will be in kilogram per second. HFG is provided, and as I mentioned, normally the value of HFG is provided so that you can use it for calculating the GOR. 2, 3, 8, 4 kilojoule per kilogram. Enthalpy of the distillate water leaving the dehumidifier, which is basically M dot D. So the enthalpy of this M dot D, which is H of MD, is given to us, and it is 235.1 kilojoule per kilogram of water. He's providing us with CP of the water as well, 4.2 kilojoule per kilogram Kelvin. The state of air leaving the humidifier, which is state 2A, this point is given to us, and we have H air 2 given 184.7, omega 2 is 0.055, and T air 2 is given as 42.14 centigrade. So these are the information given to us. The first thing we're requested to do is to sketch the cycle. It is sketched here. Calculate the temperature of water leaving the dehumidifier. So basically the components, this is our humidifier, and this is the dehumidifier. And he wants the temperature here. First thing that is needed, temperature at 0.2, which means that we need to make an energy balance for the dehumidifier. But to make an energy balance for the dehumidifier, we need to make sure that we have the relevant information that are needed in the dehumidifier. For example, we know the mass flow rates of air and water. We know the conditions of air entering and leaving the unit. We have information of water entering. We have the information of m dot water. Still, we have one more thing missing that we need to do before obtaining the temperature. Can anybody guess what is that? What is missing? Let's look at the flow rates. What flow rates do we have in and out?
Air and water.
Okay. Do we have
water, air.
Okay, do we have the flow rate of the distillate of the fresh water which is leaving here? No, this is not given. So that's something that we need to determine. So first thing that we need to do in the problem, actually it is requested as what is needed in number 4, but we have to bring it here. That m dot distillate is basically m dot air into the difference in omega, omega 3 minus omega 1. What is given to us in the problem? We are given mass flow rate of the air. Actually, we got it in an indirect way by dividing the mass flow rate of the water by 2, which is the mass flow rate ratio. What about omega 3? Do we have it? Look at the information that are given to us here. We are given for the air only 2 values of omega, omega 1 and omega 2. But omega 3 is not given. You notice that?
Yes,
Yes.
we have only omega 1 and 2.
So what do you think we can?
Omega 2
Omega
is
3.
the same as omega 3,
Yes.
isn't it?
Omega, we're talking about omega 3, same as what?
As omega 2.
Yeah, this is a very good point, Abdul Karim. And please note that when we are talking about a modified air heated cycle, whatever is going to happen here in this heater is basically sensible heating. So omega 3 should equal omega 2 for this. And this applies only for this layout, only for the air heated cycles, that across the air heated, because the air heater does sensible heating only. It does not do evaporation, it does not do condensation, only heating. Accordingly, before and after the air heater, the value of omega is the same. And omega 2 is already given to us. We know the value of omega 2. Accordingly, we can, omega 2 here is 0.05515, here is it. And omega 1 is given here. So from here, we can substitute this 0.05515 minus omega 1, which is 0.03118, and then we can calculate how much is the productivity that you can expect in this system. Now we know the MD, we can make an energy balance of the dehumidifier. that the sigma energy in is equal sigma energy out. And energy in and energy out is nothing but basically the kind of the enthalpy associated with the flow in and out. So what is in? M dot air enters in and H air 3. This is inlet. M dot water into H water 1. This is inlet. The exit is going to be M dot air H air 1, which is right here. M dot water H water 2, which is right here. This is what's needed. And M dot distillate that we have already obtained in the previous into H distillate. H distillate, which is this. You can call it H distillate or H M distillate, whatever. Now look at this equation. What are the information that we know? We know M dot air, we have calculated it. We know H air 3, it has been given to us in the statement of the problem that H air 3 is, we are talking about 226.6. So this value is given already. So we know it. M dot water we know. H water 1, what he is giving us about the conditions of water. He says that water is entering at a temperature of 30. So we know about this, that the temperature is 30, so we can make the approximation that this is equal to Cp into T1. Cp has been given in the problem as 4.2, here is it, and T1 is given as 30. M dot air, we know it. H air 1, we know the value has been given here as 112.4, plus M dot water, we have it, 0.07. H water 2, again, we're going to write it as approximately Cp into T water 2. M dot distillate, we have calculated in the previous step, and H distillate has been given to us as 235.1. So in this equation, what's the unknowns? We have only one unknown, which is, by the way, this is T. What's the unknown that we can solve here?
T water 2.
So the only unknown in this problem is T water 2, and then we can get it at that step. So this is first, and what was required is to sketch the cycle, we did. Second is to determine the temperature of water leaving the dehumidifier. Actually that was, this was request number 2, because request number 1 was to sketch the cycle. Number 3 is Qn. Let me, for example, start with Khalid. You're with us, Khalid?
Yes, I am, Doctor.
Okay, so Qn, this is Q given to the air heater, isn't it?
Right.
Which is right here. If I need to write the value of Q, what would it equal?
The value of Q.
Yes, this is what we need.
Going to be the mass, the M2A times the HA2.
That's it. We're looking for QA. Remember, what Q will do, it will increase the air temperature from this value right here to the value right here. Which means that what we have written so far is the total enthalpy of air entering. As a matter of fact, it should be M into the enthalpy difference, which is m dot into HA3 minus HA2, isn't it?
Yes, this is the total.
Exactly. We are looking for how much is the energy added to the air as it comes to the unit. So it is actually characterized by the difference of enthalpies across the unit. The air enters at a temperature of 42, and here you have increased the temperature to 80 degrees centigrade right here. So to calculate this amount of energy or rate of energy added to the air, this is what we do. And another thing here, another warning I have to do, you cannot write it as m dot air, Cp air, T air 3 minus T air 2 as the value of the enthalpy. You cannot do that. Why? You can do this only for dry air. The air that we have is not dry. It's actually have a humidity of 0.055 here. You cannot
Contains a little bit of water.
because air is carrying water vapor. It's humid, so you can simply just give it as mcp delta T. mcp delta T is only for dry air. Here we have to put the enthalpies. Why? Because the enthalpy here is a function of both temperature and omega.
Okay.
Doctor, the same goes for if it's a water heated system, right? Qn. Instead, in this case,
Yes. I mean, in the HDH cycles, you can never treat the air as dry air so that you can apply this equation. You cannot apply that equation at all, because air is basically humid air. Number 4, we are supposed to be calculating the rate of fresh water. And let me check here if I call, for example, for Badr. Badr, are you with us? Badr? Okay, he does not seem to be. Badr Saad. Okay, so who else can tell me? What about this? Do we have to calculate this value or not?
this is already given.
Yes,
We
this
have
value has already been calculated, and we have calculated here in that step. So basically, the value or the value of this m dot distillate, we needed it in the analysis of the dehumidifier, and it has been calculated over there. So this has already been taken care of.
Doctor, a question regarding the. So basically, M prime is the same as the M distant, right? I mean,
Yeah,
they both.
What is it again?
They both produce sweet water, right?
What is distillate? You said what is the same as the distillate?
The brine.
No, the brine is here.
I know. I mean the amount. They both produce sweet water.
Sweet water is produced only here.
So the brine is only rejecting the water.
Brine is rejected. We are throwing it away.
Okay.
But this is what we are getting as, this is the product of the whole cycle. This is why we are doing the whole cycle, just to get this quantity of water in.
Good.
This is something that we are thrown away. The brine is thrown away. And actually this is basically making some sort of an environmental problem, because the brine which is rejected normally, it is rejected at higher salinity, and the higher salinity people are concerned about it for the marine life. And they are talking about ways so that they will do some reuse of this, maybe by further operating it in another cycle, until it is very much concentrated, and then they crystallize it and get the salts and sell the salts, which actually has much higher value than the water.
Doctor, I have a question here.
Yes, go ahead.
Is the brine water that is being rejected to the environment, is the quantity so significant to the point that it will affect the environment?
Actually, for a single plant, it is not. But look at the Gulf. How many desalination plants are there for Kuwait, for Qatar, for Saudi Arabia, for United Arab Emirates, and for Oman? All of these have large number of desalination plants, and all of the desalination plants are rejected the brine into the Gulf. And the Gulf is semi-closed. From the top, it's closed. From the bottom, there is a small opening, which is at Hormuz. You see? So
Yeah.
considering that it's an almost a closed body of water, then there is evaporation of the seawater from the sun. This is number one. Number two is the dumping large quantities of salty water or brine into it. Definitely there is a link between it and the Indian Ocean, but is the rate of renewing the water in is equal to the rate of brine added into it? That's a question which is important. We used to deal with it as a mass sink. Whatever you add into that, it's not affected. But eventually with time, I think you can even see that salinity of the water in the Gulf is about 50,000, almost. It ranges between 46 to 51,000 ppm. Whereas when you look at a place like the Atlantic Ocean, it is 28,000. So there's a difference here. We are talking about twice the salinity of the Atlantic Ocean almost here in the Gulf.
Right, thank you.
Now, our next part which is needed is the gore. So number 5. Should be the system gore. Gore by definition is m dot distillate into HFG divided by QN. What do we have here? We have m dot distillate. We have calculated in step number 1, and it is also as a part of step number 4. HFG is provided to us. The value is given as 282384, as you can see it here. And QN has been calculated in step number 3. So now we are in a position that we can calculate what is the system gain output ratio. Clear, ya shabab? Any question?
Yes, Doctor. HA3 is given to us.
Yes, here I just follow my arrow here. Normally, in problems like this, you are given the value of HFG so that you can calculate it for gore calculations. Now, the next thing that we need to calculate is the brine temperature as it leaves the humidifier. So what I'm going to do is that I'm going to probably erase here.
Doctor, one question.
Yes.
So basically, we apply the same procedure if it was water heat.
Yes, it would be the same procedure
Just replacing
for a water heated cycle.
Isn't it?
Exactly. The only thing is that there we are heating the water rather than heating the air. So that for water heated cycle, this is going to be different because you will be heating the water. So it will be flow rate of water into enthalpy difference. For the water, we can write it as Cp delta T. That's not a problem. Now, looking at the energy balance for the humidifier. Again, for the humidifier, there is a quantity. We need the value of m dot brine. It has not been given to us. So this basically is equal to m dot water minus the quantity that has been carried by the air, which is m dot air omega 2 minus omega 1. If you notice that theoretically speaking, this is the same value as m dot distillate. Remember, omega 2 and omega 3 are the same. So that represents basically m dot distillate. Now, for this problem, we have m dot water, 0.07. We have m dot distillate, we have calculated it, so I can get the value of m dot brine. Then, energy balance for the humidifier, sigma energy N is equal to sigma energy out. Do we have battery back or not yet? Looking again at the humidifier, we'll get flow rates in and out. We have m dot air into H air 1. This is energy, this is flow rate in. There's another float of water that needs to be sprayed here, m dot water, H water 2. This is equal to whatever is leaving will be m dot air, H air 2, and we have m dot brine, H brine. So we have air entering here at this point on the figure, and air leaving at this point on the figure. So this is 1 air and 2 air. We have calculated it in the terms of energy in and the energy out. And there is water coming in at that point. And there's brine leaving at this point. So these are the associated flows in and out of the system. And this is how we wrote it. If you remember from Therm 1, this is very much the same as writing an energy equation for a heat exchanger. But remember, the humidifier is a heat and mass exchanger. The equation will not change. What is going to change is that we know that the enthalpy of the air in and out is essentially dependent on temperature and humidity. Otherwise, the control volume analysis as a closed box, it's basically the same. Now, what do we know? We have m dot air, 0.035, which is half of m dot water. H air 1 is given to us in the problem. The value is given here as 112.4 kilojoule per kilogram. M dot water is given to us, 0.07 kilogram per second. H water 2 is basically, or it's approximately as Cp into T water 2. We have calculated T water 2 previously. M dot air is known. H air 2 is known to us. The value is given here, 184.7. M dot brine we have just calculated here. So the only thing which is unknown here is H brine. So from this equation, we can calculate H brine, which is equal almost to Cp water into T water 3. And T water 3 is what we need in this problem. So the energy balance for the humidifier would enable us to calculate the exit water temperature. Now, last thing, yes, go ahead.
When applying the, do you hear me clearly?
Yeah, I can hear you. Go ahead.
Because I have the internet connection.
Yeah, the sound.
Appears. Anyway,
the sound sometimes is not clear, but I can hear you now. تفضل يا خالد.
Cool. So when applying the mass balance, I'm not talking about the energy balance. We always consider the air ratio, right? Omega, we have to include it. So for the air, I mean. This
No, for the air who are ordering, yeah, for example, if you are going to consider air in the humidifier, the inlet and the outlet are the same. Why? Because when we are looking for the mass balance, and remember the mass balance for the air, we are considering the mass flow rate of
dry air.
dry air. This is for the mass balance. For the energy balance, I have to account for the humidity.
So how about number 6? We did the mass balance, right? And we
Number 6, we did the mass balance for the water.
Okay.
Look
So
at what's happening here. I have quantity of the water which is being sprayed here. Part of this water is carried by the air which is moving here. So the water which is going to leave here is going to be less than the water given or entering. Where's the rest? The rest has been carried by the air.
Okay.
So air is dry air, but we make balance for the water through how much has been carried by the air. So it's coming in the balance of water. And remember, this is the same as we did in the dehumidifier. We said there's a mass flow rate of dry air coming in, mass flow rate of dry air leaving here, and there is water that has been condensed out right here. And that's why we're writing the energy balance here. We have considered the mass energy balance of the air energy balance of the water, and the quantity of fresh water which is being produced here.
All right, thank you.
The evaporation process is taken care of by looking at the mass balance of the water in the humidifier, basically. Did I answer your question?
Yes, Doctor. Another question, if you allow me.
Yeah, sure.
So for the mass balance, we have to consider whether it's for water or air. But for energy, we applied for energy balance. Energy equation, we applied for that system. So we include both air and water.
Let me rephrase your question. The mass balance, normally we consider the mass balance for the water because we assume that dry air is the same. So when you are considering, look at this. This is a mass balance inside the humidifier. Mass balance for what? Only for water. If I need to make a mass balance, a total mass balance for the humidifier, I should have written it as m dot air plus m dot water at 2. This is air at 1 plus m dot water at 2 entering. This is equal to m dot air at 2 plus m dot brine. But here you'll find m dot air, the dry air is basically the same. M dot water 2 is not the same as the m dot brine. So here I have to add m dot air into omega 2 minus omega 1. M dot dry air is the same, so we cancel it. That's why we don't put it into the equation here. What you see here is the equation written up there. So I've canceled out this because the dry air quantity is basically the same. But when it is leaving, it is carrying some water vapor, which is taken care of by here. And this is how the brine is less than the flow rate of the water by this quantity that the air has taken out.
Clear.
Khaled?
Thank you, Doctor. Yeah, it's clear.
Okay, now let's continue. What is needed now is the energy balance, is the effectiveness of the dehumidifier. We can calculate it based on the air side, and we can calculate it based on the water side. We're talking about the dehumidifier. And for the dehumidifier, air enters at H air 3 and it leaves at H air 1. This is delta H in the humidifier. Delta H maximum is m dot air, H air 3, the inlet point does not change, minus H air 1 ideal. Now, who remembers what is H air 1 ideal?
Temperature of the inlet of water.
Exactly. So this is enthalpy of the air at T water 1. This is the lowest temperature that air can be cooled to inside the unit. Air is entering at 80 degrees centigrade and it will cool down. Water is entering at 30 degrees centigrade and it will heat up. The lowest temperature ever that air can be cooled to is the temperature of the inlet water if we assume that the size is infinity of the unit. So we're going to cool air to the lowest possible temperature. And this value is given to us actually in the problem statement. If you go back to the problem, it will say how much calculate the dehumidifier effectiveness if H air ideal is 99.7 kilojoule per kilogram. And from here, we can calculate the effectiveness of dehumidifier for the air side. Now we can calculate the effectiveness of the dehumidifier at the water side. And this is going to be, we're talking about the dehumidifier. So across the terminals, we have m dot water into H water 2 minus H water 1. This is the actual case over m dot water. Water is going to be heated. So H water 2 ideal minus H1. We have these values, m dot water, H water 2, H water 1. The only unknown is H water 2 ideal. This value is given in the problem. Actually, it's telling me in that problem statement that H water ideal is basically 335. But now I can ask you, what does this temperature represent? It represents H water at
Water inlet. The
No.
maximum temperature.
That's
This
it.
water is going to be heated.
It's not the water inlet. What will happen to the water inside the dehumidifier? Water is going to be heated up.
The air inlet.
Exactly.
inlet.
So it's going to be, ideally speaking, if the size of the unit is infinity, then water will be heated until the maximum temperature ever in the cycle. What's the maximum temperature ever? It's the inlet air temperature, which is the 80 degrees centigrade. So this is basically is T air 3. Now, our effectiveness should be the maximum of these two values. Now, I'll probably remind you of something I've done last time when we were talking about this issue of calculating the effectivenesses, and normally what would happen in units like this. We have considered that it is basically sort of a counter current arrangement device, and accordingly we have water coming in and water leaving. So if I need, for example, to draw the relation between temperature and the distance. Then let's, for example, take the dehumidifier, the one that we are considering in. What is hot? Air is hot. So air is going to enter here and it will cool down to a temperature. So this is basically T air 3 in our case, and this is T air 1. Water is going to enter at a temperature of about 30 degrees centigrade. So this is T water 1. And water is going to be heated to the exit temperature, which is T water 2. Now, we look at this unit because we need to determine the maximum and minimum. The maximum temperature in the unit is here, which is the 80 degrees centigrade. The minimum temperature is here, which is the 30 degrees centigrade, and this is Tmin. So this is going to help me in determining the values of the maximum enthalpies here. Air is going to be cooled down. If the system has infinite area, air can be cooled down to this temperature if the effectiveness is 100%. In reality, that does not happen. But this is the way that we do for comparison. And this is the same idea of the effectiveness of a heat exchanger. As I told you, they are the same, but here the difference is that it's a heat and mass exchanger. The effectiveness for a heat exchanger is the actual difference in enthalpy divided by the maximum difference. If we are talking about heat exchanger that has water in and water out, then that basically can be the maximum temperature difference. So in the heat exchanger, we used to write it as T air 1 minus T air 3 minus T air 1, or let me put it in terms of water, that the inlet temperature over minus the outlet temperature divided by the inlet temperature minus the lowest temperature. So it's delta T over delta T maximum. This is for heat exchangers. For us now, it's a heat and mass exchanger. So instead of talking about temperature, we are expressing it in terms of enthalpies. So that's the way that it goes here. So accordingly, you can look at it this way. This is temperature of the air in, actual. This is temperature of the air out, actual. What is the maximum possible? It should be the lowest temperature here, which is this temperature. Same thing for the water. Water enters at T water in, T water 1, it leaves at T water 2. If the system is infinitely large, then this T water 2 is going to increase more and more and more and more. The highest value is this. So when you are looking at delta H maximum for the water side, it would be the enthalpy of the water at this temperature minus the inlet enthalpy of the water. So that is something I hope that would help, so that you would always remember what we mean by writing this, this expression of the effectiveness. There was something I was talking about last time, is that we are lately not considering this kind of expressions for the effectiveness of air putting of the humidifier or dehumidifier, and calculating it as a sort of what's the effectiveness for the air side, the water side, and then doing a comparison to see what's the maximum value, or rather doing something else that we call based on the difference of enthalpy between the two streams inside the unit. For the humidifier, for example, what we expect to happen is, let me change this to a pen. And what I'm saying here is something that you will not see in an exam, so it's okay if you don't get it all. Here we are talking about, for example, enthalpy change versus distance. For the water in the dehumidifier, which is this. What happens? Water's inlet enters at a low temperature, right here, and then increases in temperature, like that. But for the air is being humidified, which means that the value of phi for the air is always equal to 1 everywhere. We have reached it for the dew point for the air, and it starts to condense the water vapor in. The profile for the air is basically looking like this. So when we are looking for the differences of enthalpy, you'll find that the smallest enthalpy difference is occurring here. The enthalpy difference inside the unit, within the unit, is a little bit bigger. So when we are looking for the effectiveness value, I'm looking for that minimum differences, and the minimum differences are here. So the effectiveness of the dehumidifier is going always to follow this the same procedures that we have taken earlier. That what are the enthalpy at the inlet, enthalpy at the exit, and we're doing this kind of comparison. For the humidifier, it's a little bit different, because for the humidifier, water is hot and air is cold. See, this is the highest, this is the line for enthalpy of the air inside the unit. This is the line of enthalpy increase for the water. Water is cold and air is hot. That's why we have it this way. In the humidifier, it's not like that, because in the humidifier, water is hot and air is cold. Because water is hot, then we expect the line to be something like this. In the humidifier, the differences here at the terminal does not represent the maximum enthalpy difference. The minimum enthalpy difference. The minimum enthalpy difference here is located somewhere in the middle. And that what we call the enthalpy pinch is going to be determined somewhere here. And that becomes a little bit of a challenge, because you cannot just determine it when you are looking at the figure like what we did for the dehumidifier. I don't want to confuse you here, but what I want to say is that when we want to get a more precise calculations of the effectiveness of the units, then we better look at the enthalpy pinch, which is a little bit challenging when we are looking at it in the humidifier. We cannot just put it or calculate it by looking at the figure as is, but there's some additional effort that we need to do. But this is why, for our case here, as long as we are concerned in this course, what we are going to do is to consider the enthalpy by the way that we have written before. We are considering enthalpy for the dehumidifier at the air side, considering at the water side, and then compare between them. Take the highest. The same thing for the humidifier. We are going to consider effectiveness of the humidifier at the air side, effectiveness of the humidifier at the water side, and comparing between them to get the maximum. And basically, we are considering the points at the inlet and exit of the unit. So we have the terminal values. These are the values that we calculate, and we write our value of the effectiveness based on that. And this is exactly what we have done in the previous example. Are there any questions? Okay, now let me check. I did not check the attendance so far. I'll just call your names quickly. Rashid Eliami. Abdullah Al-Azwari. Muhammad Al-Ghamdi.
Yes, doctor.
Ahmed Hussein.
Yes, here, doctor.
Okay. Hussein Al-Maslami.
Yes, here.
Okay. Hadi Al-Utaybi.
Yes, doctor, yes.
Okay. Abdul Karim Ramadan.
Yes.
Badr Safar.
Yes, doctor, yes.
Badr, I called you several times before and you were not there.
Yes, doctor, I heard you 2 times, doctor. But I was using other device and microphone was not able to connect me with you.
Yeah, in such state, just make sure that you are with me. You can text.
Yes.
Write to me that I'm here, but I cannot hear you, because this way I may consider you absent.
No, doctor, I have heard you. You asked me about
So
mass flow rate first time, and second time you asked me about energy balance, I think.
So I'm telling you
But I
now
was not.
that I might be calling any one of you at any time. If you don't respond to me, I'll consider that you just opened your PC and you left.
Okay, doctor, I'm sorry.
Okay. Saleh Safar,
Yes.
Osama Shahrani,
Yes, doctor, I'm here.
Khalid Shamrani,
Yes, doctor.
Sultan Suwalim,
Here, doctor, yes.
Abbas Yahya,
Yes, doctor.
Hussein Yusuf,
Yes, doctor, here.
and Dawood Al Haji. Dawood.
Hear me?
Oh yes, I can hear you. I mean, your voice is a little bit far, but we can hear you. Okay. Okay. So what we may be getting into is now turning our attention to